This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on curve sketching. We are given the function f of x is 2x minus 6 over x minus 1. We want to sketch the curve of that function, and we're going to use the following information to do that. The domain of the function, the y-intercept, the x-intercepts. X-intercepts are sometimes difficult to find, but if they're reasonable, we'll use those as well. We'll find intervals where the function is increasing and decreasing, local mins and maxes if we have any, intervals where the function is concave up and concave down, points of inflection if we have any, and asymptotes. So we're going to collect all this information, then put it together to sketch the curve of that graph. So we're beginning with this function. F of x is 2x minus 6 over x minus 1, and we are interested in the domain of the function. Recall that you cannot divide by 0, so x minus 1 cannot be 0, x cannot be 1. So our domain is all real numbers except 1. If we're going to consider that an interval notation, that would be the interval from negative infinity to 1, together with the interval from 1 to infinity, and we write it that way, putting a union sign in between those two intervals. So that's our domain of our function. All real numbers except 1, interval from negative infinity to 1, union in 1 to infinity. We're going to rewrite this as y equals 2x minus 6 over x minus 1, and we're going to consider the intercepts. The first intercept I'm going to ask for is the y-intercept. And if a problem is written in function form, finding the y-intercept is relatively easy. You set x equal to 0 and solve for y. Setting x equal to 0, 2 times 0 minus 6, 0 minus 1. So we're going to get y is negative 6 divided by negative 1, or y is 6. When we set x equal to 0, the y value is 6, so our y-intercept is 0, 6. Now this one's not too bad. We're going to go ahead and find the x-intercepts as well. In that situation, we set y equal to 0 and solve for x. So again, rewriting it in that form, in the xy form, rather than the f of x form. To find the x-intercept, set y equal to 0 and solve for x. So we're going to get 0 equals 2x minus 6 over x minus 1. If a fraction is 0, the numerator is 0 and the denominator is not. So 2x minus 6 is 0, 2x is 6, x is 3. So setting y equal to 0, we only get one x-intercept. That happens when x equals 3. So x-intercept at 3, 0. So we have 2 points on the graph. We have the y-intercept on the graph, and we have the x-intercept on the graph. Now looking at this function, what's our next move? We want to find the derivative, because we're going to use that derivative to determine on which intervals is the function increasing and decreasing. This is a rational function. I need to use the quotient rule to find the derivative of this function. So u, the numerator, is 2x minus 6, u prime is 2. V is x minus 1, v prime is 1. And we know the derivative using the quotient rule is u prime v minus uv prime over v squared. So to find the derivative u prime v, 2 times x minus 1 minus uv prime minus 2x minus 6 times 1 over v squared over x minus 1 squared. Simplifying this, 2x minus 2, and then distributing this minus sign, because the times 1 is just going to give us that, minus 2x plus 6. So 2x minus 2 minus 2x plus 6, distributing that minus sign, over x minus 1 squared. And you'll notice 2x minus 2x is 0, negative 2 plus 6 is 4. So my f prime of 6 is 4 over x minus 1 squared. And we are looking for intervals where this is increasing and decreasing. We look for critical values and recognize that that derivative is never 0. For a fraction to be 0, the numerator has to be 0. That never happens. So there are no points where the first derivative is 0, but there is a point where the first derivative doesn't exist, and that's at 1. So we'll state that f prime of 1 does not exist, so 1 will act as a critical value. We will choose numbers on either side of 1 to determine if the function is increasing or decreasing. So we set up a number line. 1 is our only critical value. We're going to choose representatives of this interval and of this interval. To the left of 1, I've chosen 0. To the right of 1, I've chosen 2. Now we're going to plug those values into the function to see if it is increasing or decreasing. If I plug 0 in for x, 4 over 0 minus 1 squared is 4 over negative 1 squared. Negative 1 squared, of course, is positive 1, gives us 4. Which means on this interval from negative infinity to 1, this function is increasing. So I like to draw an arrow there to emphasize that. Now, when we're at 2, f prime of 2, plugging 2 into this function, 2 minus 1 is 1, squared is positive 1, 4 over 1 is positive 4 again. So indeed, that function is increasing on that interval as well. So it's increasing on the interval from negative infinity to 1. It is increasing on the interval from 1 to infinity. But it's not increasing at 1, so we have to pull that point out. So we say the function is indeed increasing on those two intervals, negative infinity to 1, union 1 to infinity. The next piece of analysis we want to do is regarding the second derivative to see where the function is concave up and concave down, to see if there are any points of inflection. You can see with this increasing, decreasing situation, there are no minimums or maximums for us to work with. So looking at f prime of x, 4 over x minus 1 squared, I'm going to rewrite that as 4 times x minus 1 to the negative 2 to make it a little easier to find the second derivative. So f double prime of x is the derivative of the first derivative. The derivative of f prime, the derivative of 4 times x minus 1 to the negative 2. Of course, we can pull the constant in front of the derivative operator, 4 times the derivative of x minus 1 to the negative 2. And this requires the chain rule. Pull the negative 2 down in front. It'll be negative 2 times the inside, x minus 1 to the negative 3, times the derivative of the inside. And it's, there we go, negative 2, x minus 1 to the negative 3, times the derivative of x minus 1. But the derivative with respect to x of x minus 1 is just 1. So we get 4 times negative 2 times x minus 1 to the negative 3 times 1, which 4 times negative 2 times 1, negative 8, x minus 1 to the negative 3, or negative 8 over x minus 1 cubed. There are no points where the second derivative is 0, but there is a value where the second derivative does not exist. That, of course, is when x equals 1. So we make that point, f double prime of 1 does not exist. So we will check the concavity on either side of 1 to determine intervals where this function is concave up and where this function is concave down. So there's our second derivative, our potential inflection point, the place where the concavity may change, is at 1. So we lay out our number line and we pick representatives of either interval. To the left of 1, I will pick 0. To the right of 1, I will pick 2. And we will plug those into the second derivative function and see how that behaves. So plugging 0 in for x, 0 minus 1, negative 1 cubed is negative 1. Negative 8 over negative 1 is positive 8. So if that's the case, on this interval, the second derivative is positive. So on this interval, the function is concave up. It's concave up on the interval from negative infinity to 1. So knowing that, we know that it's bending upwards somehow. So I'd like to put a parabola bending upwards to emphasize that fact, that on that interval from negative infinity to 1, the function is concave up. Now plugging 2 into the second derivative, 2 minus 1 cubed is just 1, negative 8 over 1 is negative 8. So the concavity at 2 is going to be different. Since the second derivative at 2 is negative 8, we know the function is concave down on the interval from 1 to infinity. So if we draw our little parabola there, that would be an upside down parabola. That's concave down. So we have all of this information. We want to use it to construct a graph by hand, piecing all of this together. So here's our original function. We said f of x is 2x minus 6 over x minus 1. Let's find our asymptotes. Vertical asymptote. Bottom is 0 when x is 1, and that doesn't divide out on top. If you have a situation where the discontinuity does not divide out, that will be a vertical asymptote. So that's good to know. vertical asymptote when x equals 1. The horizontal asymptote is determined by looking at what happens to the function as x goes to infinity. So to find our horizontal asymptote, the limit as x goes to infinity of 2x minus 6 over x minus 1 to do that analysis. You may be able to see that that is going to be 2, since the highest power of the top is 1, the highest power of the bottom is 1. Looking at the coefficients, 2 divided by 1 is 2. If you want to be a little bit more formal, divide top and bottom by x, 2x over x minus 6 over x over x minus 1 over x. We get the limit as x goes to infinity of 2 minus 6 over x over 1 minus 1 over x. 6 over x goes to 0, 1 over x goes to 0, 2 minus 0 over 1 minus 0, or 2. So the horizontal asymptote will be at y equals 2, and the vertical asymptote will be at x equals 1. And when we construct a graph, that is going to be important for us to know where those asymptotes are, so much so that I almost put them on first, close to first. So let's look at all the information we have. We have the domain, everything but 1. We have an x-intercept at 0, 6, an x-intercept at 3, 0, a y-intercept at 0, 6, 2 points on the graph. It's always increasing except at 1. It's concave up on the left, concave down on the right. Vertical asymptote at x equals 1, horizontal asymptote at y equals 2. So how are we going to graph this? I have the y-intercept 0, 6 and the x-intercept 3, 0. So that's what I always start with, 2 points on the graph. 0, 6 here, 3, 0 here. If you want more points, you certainly could plug in more values for x. You could plug in x equals 4 or x equals -1, and you could see what those points would be. So if you're ever short on points, you could always add some. But I think this might be enough for us to start with. And the next thing I'm going to look at are the asymptotes. So I have these 2 points. I have an asymptote x equals 1, that is a vertical line. I have an asymptote y equals 2, that's a horizontal line. So together with those 2 points, I draw in those 2 asymptotes. Vertical asymptote x equals 1 here, horizontal asymptote y equals 2 here. There's our point 0, 6, there's our point 3, 0. Now we also know where the function is increasing. We also know where the function is concave up, concave down. So what did we say about increasingness? We said it's increasing on the interval from -infinity to 1, from here to 1. It's increasing from 1 to infinity. So the roller coaster is always going up. The roller coaster is always going up. So that may start to give you an idea what this graph is going to look like, together with its asymptotic behavior. So it's increasing here, it's increasing here, always going up. We also had concavity. We said it was concave up, so it's bending upwards. The parabola is bending upwards, -infinity to 1, bending downwards, 1 to infinity. So knowing all of that, can we construct a decent graph? Always increasing, concave up on the first half, concave down on the second half, going through the points 0, 6, and 3, 0, with these things working as asymptotes. So the goal is to think about what that graph would look like. And here we go. Notice increasing on this interval. Roller coaster is always going up from left to right. Notice increasing on this interval. Roller coaster is always going up from left to right. Concave up here. Concavity is positive. It looks like a positive parabola. Negative concavity here, bending downwards. And then you also see the asymptotes. The horizontal asymptote at y equals 2 is here, and the vertical asymptote at x equals 1 is there. And that will conclude this lesson.